Good morning. Thank you so much, Dr. Zahra, for the introductions. So my name is Hanafi Damanhuri, the project leader. Would like to sampaikan salam from Professor Dr. Dewan. She's unable to come for the presentation today, so I will be giving the presentation on behalf of our group. Okay, the title for my presentation today is basically the title of our project or grant. We would like to unravel the traditional events of normal to pathological aging leading to cognitive decline. Just a bit of overview for my presentation. I will give some introductions on the topic that we would like to study. I have a data from our human study, I have a data from a rat study, and if you have time, I will try to touch a bit the data from our mouse study and also the conclusions so far that we have. Okay, just a bit introduction about the aging. I think we have heard a lot of facts from the previous presenters, from Professor Ng before this, from Iceland and so on. And we know that aging is a big problem to our community. It's not only in the world, but it's also in Malaysia. So if you look at these figures, here, from 1950 to 2000 to 2050, it is projected that by 2050, the group of elderly will increase significantly, whereas the group that are between 0 to 19 years old is getting smaller and smaller. This is basically the imbalance of our community. And Malaysia will also evolve with this phenomenon. We have the same pattern, and basically this is a big burden to our community as well. We know that a lot of diseases is associated with aging, but for the purpose of today's presentation, we are only interested with the brain aging. So brain aging basically will affect the cognitive function, leading to the cognitive decline, and this is basically the deficits in terms of the global cognition and mental capabilities. This is, can be visualized by declining of the several functions such as memory, executive functioning, attention, and also language as well. This is a very big diagram and graph. I think a few presenters have presented about the same pattern, whereas if you look at when we age, there will be a cognitive decline happen in our brain. We can't get away from that. But the main thing is, we want to know whether is there any point that we would know the cognitive decline deteriorating, meaning that it's getting worse and worse. Where the worst case scenario, we will develop dementia, or in some patients will develop Alzheimer's disease. So basically, cognitive decline is a normal. In a normal cognitive decline, is basically a process that can lead to cognitive impairment. In a severe form of cognitive decline, will lead to formation of Alzheimer's disease and dementia. In the elderly, the cognitive decline can represent a normal change associated with the aging process or early signs of impairment or dementia. So there are few risk factors for cognitive decline. Of course, Dr. Iceland has explained well extensively in the previous presentation regarding how our lifestyle and our environment can affect the cognitive functions. If you look at this sign here, low education level, social network, depression, anxiety, and stress. So this is all the environmental factors that can affect the cognitive decline. But at the same time, there are also a few biological and genetic factors that can lead to cognitive decline as well. Of course, the interest of our project and our group, this has been a while that we have been doing this, and we are interested in terms of to see whether oxidative stress can lead to cognitive decline. Just a bit of brain aging. it's basically increased damage by free radical. When you have a brain damage, your brain starts to get shrunk, and then you can see deterioration in terms of neuronal and then the neurotransmitters functions. We can see some problems in terms of the blood vessel development. So there's increase of inflammations. In the elderly, you can see a lot of bioformations, and also in the Alzheimer's state, you can see accumulation of amyloid plaque and neurofibrillary tangles. So this is basically will lower the information processing and also retrieval. So this is kind of indicated as a cognitive decline. Again, just to touch a bit on the mechanism of brain aging, we postulate that there's increase, once you start age, there's increase in terms of the active oxygen species. You can see a lot of cognitive damage in the brain, which includes the DNA damage, protein damage, and also the lipid damage. This may lead to mitochondrial dysfunctions that can lead to inflammations, and at the same time, the oxidative damage itself can lead to synaptic loss, neuronal apoptosis, and then this is also leads to white matter degradations. So all of this can lead to brain shrinkage, affect the cognitive impairment, then in the worst case scenario will lead to neurodegenerative diseases. So the main questions that we would like to ask is there any point from the normal aging that can turn into pathological aging? And if yes, where could we start intervention if possible? So I'll start off by sharing with you guys a bit of our data from the human study. So this is the experimental design. We screen our subjects. We have 4 different groups from 4 different age. We have subjects at the age of 30, 40, 50, and 60. The total number of subjects is just 40. Okay, I know this is quite small, but we can't get away from that. And then we measure the cognitive functions by the same neuropsych test, MSE, MOCA, digit span, digit symbols in the box. Additionally, we also check the brain activity by looking at the electroencephalogram, EEG, and also the functional MRI. We collected the blood samples, and we look at the general health status. This is very important because our subjects, we want to maintain in a specific group, so we must ensure the subjects that we have is healthy subjects. So we also measure the oxidative status, and then after that we proceed with the gene profiling and protein profiling. Okay, so this is our inclusion and exclusion criteria. So in the inclusion criteria, of course, the individual must be between 30, 40, 50, and 60 years old. We chose today as our subjects, the years of education between 6 to 15 years. It must be non-smoker. And the education background must not higher than degree, again, just to eliminate any confounding factors. For the exclusion criteria, of course, we omit for subjects that are smoking, pregnant females, have diseases, had surgery for the last 6 months, non-Malay, alcoholic, under medication or taking house supplementations, colorblind and hearing problem. This is 2 main things that we have to consider because part of the cognitive task is to use your visions and then your hearing. Okay, and then in terms of the individuals with implants and claustrophobia, this is mainly because for the MRI. This is the flow of participants. We have screened 1,526 subjects. Unfortunately, 1,280 does not meet the requirement, so we can't put them in the study. 246 subjects have been shortlisted for the study. So we have screened 193 subjects, 160 passed the full blood test, and then so far we have looked at 71 subjects for the cognitive test. In terms of demographic data, if you look at from the age, we are quite consistent in terms of the age, and we have a mean of 30.38 for the age 30, 40.8 for the age 40, 49.17 for age 50, and then for the above 60 for 66.1. So it's quite clear separation between groups. In terms of years of the educations, it's not as consistent as we expected, but if you look at the age over 60, we can't get away from this. This is the subjects that we can look at. In terms of the lipid profile, it is healthy. Okay, so and also in terms of the glucose level, it must be healthy as well, because this is the first criteria before they can be enrolled into the study. We look at the MSc and MOCA. These two studies specifically to assess the short-term memory, executive skills, attention, working memory, language, orientation. So, this is been divided into scores, a total of 30 scores. So for us, we take 24 as our minimum score. So any scores below 24 is considered as has the cognitive impairment. So apparently with the MSE, we couldn't see any. You can see some differences. There's a pattern there, but if we talk about the kind of score that we have set, it seems like the H3 is still not too bad because it just is still past the 24 marks. But for the MOCA, when we look at MOCA, if you have to understand that MOCA is a bit more deeper, and then I think from my understanding, it's a bit more tougher if you give it to subjects. So if you look at MOCA, you can see only age 60 that reach below 24, and in fact age 50 is just past the 24 marks. So this is some indicators that there's a cognitive impairment as early as 50 years old. And then from this data, we could say at least at this point, MOCA is more sensitive in MSE, in detecting cognitive impairment in our subject at least. So the next study that we have is digit span. So this is basically a study to look at the attention, and we have two types of digit span: forward digit span and reverse digit span. So for digit span, basically we have a digit numbers, and we ask our subjects to recall the numbers again, just to test the memory. And then for the reverse digit span or backward digit span, basically you are testing two things. We were testing the memory and also the processing, because we align numbers in backward, so they have to put it all together. It seems like in terms of the forward recall, we couldn't see much difference between groups that we have. But if you look at the backward digit span, it's so nice to see how starting from age 50, you can see a decreasing scoring, and in fact the 60 has a significant decrease compared to the age 30. And the last one that we have is the digit symbols. Again, this test is to process speed and learning and memory. We have the same pattern, and this one we can see the significant difference as early as 40 years old. Okay. We have another one. Okay. So this is basically to evaluate the verbal memory deficits. This is very interesting because we have 15 words that we give to the subjects. We ask them to repeat back after 2 trials. And for trial 1, it seems like not much difference between groups because they're just about to know the words that they have to memorize. But once you give multiple trials, and you can see they can memorize more and more words after few training. Apparently, for group 60, after the 5th trial, they still can't memorize much words as compared to the other 3 groups. And in fact, after a delayed recall, basically you give a training and then you interrupt the training by giving some, something else, things that they have to do, and then you ask them again to repeat what the words that you have trained them. And you can see clearly at group 60, you have a nice decrease pattern. At this point, we could confidently conclude that the subjects that we are dealing with, we have a cognitive impairment, may as early as 50 years old, but for sure for the 60 years old group, we know they have some cognitive impairment. In order to look at the functions of their brain, we do some functional MRI using a stroke test as our stimulus. So this is an example of images that we have. This is the activated brain regions, colored by the red color. I'm not sure if you can see it clearly from back. We can see these 2 regions is activated following the stimulus that we give. This is just an example from 30 years old subject. We also look at the oxidative status due to limitation of time. I'll just share the data that we have from the image analysis, and we have quite a nice pattern from 30 up to 60 years old, where we can see as early as 50 years old, we can see a nice significant level of increasing DNA damage as compared to the group 13. Okay, as a summary, the level of cognitive impairment is greater as the age increased. This is potentially associated with the level of DNA damage. So the next step is to complete the brain activity analysis, and of course, we'd like to proceed the gene and protein profiling in the blood of the recruited subjects. The next study I would like to explain is the rat study. I don't think you can see it clearly from the back, but this is a data across different organisms. This is C. elegans, it's a worm, cacing. This is the rats data, and this is the Homo sapiens, which is human. You can see across different organisms the nice genes that is associated with the aging, which is the oxidative stress response genes. So from there we could we know that we could use rat as our study. So again, the same principles from aging will affect the brain function, and in the end will develop the disorders. We concentrate on 3 different brain regions: hippocampus, striatum, and medial prefrontal cortex. These 2 regions has been well accepted in the literature, involved in the cognitive functions. This is our design. We have 3 months, 14 months, 18 months, 23 months, and 27 months, which is mimicking the age of the human study. So this is representing the 30, 40, 50, and 60 years old. Okay. So we also look at the cognitive function for these animals. We do extra study looking at the brain MRI to see is there any structural changes in terms of the brain as the animal age. We collected the brain tissue, and then we continue with the gene, protein, and metabolite profiling, and we also look at the oxidative status for this stress. So this is just the test that we have. We have an optical test, mercedes test, and object recognition test. In terms of the optical test, we have data from the rearing. So you can see again nice data from the 3 months, which is young rats. As compared to the old rats, you can see a nice pattern of declining rearing, and the same pattern for the duration as well. So declining rearing indicates decreased exploratory behavior and increased anxiety. In terms of the mercedes, this is for place and trip navigation. We can't see much at this point, except for the 3 months. You can see a bit different from the other groups. But if you move to the other, again, mercedes, but different parameters, which is a probe test. You can see a nice pattern again, and you can see clearly from 3 months is simply different from the 27 months. Okay, so this another test, we look at the object recognition test. So basically, we give these animals a few objects. So the objects is basically referring to this animal. If the cognitive function of this animal is intact, they will respond accordingly, meaning that they will like a new object. But if the cognitive is impaired, so they will start to not really care much about the novel object. So again, if you look at between the 3 months, this is the novel object data. Compared to the 27 months, you can see again a nice declining data. And again, the data indicate that the lower time for novel and abstract objects will indicate lower exploratory behavior. Okay. Just to link the data from human and animals, we look at the oxidative status. Again, due to the limitation of time, I'll just show you the level of DNA damage. When we do the level of DNA damage, you can see a nice pattern again. This is very similar to the data that we have in the human. In 3 months old, it's very, very minimal DNA damage, and once you get age, you can see a high increase, more than 10% increase. Okay, this is just an example of images from the brain MRI. We perform this using a 7 Tesla MR scanner. We use a free software, and then the analysis are ongoing at the moment. And just to show you a bit of what we can see from this data. So this is the specific brain regions. This is for the middle of the cortex. This is for striatum. This is the hippocampus. So we hope that between 4 different age groups from the animal, we could see some differences in terms of the structure for this animal. Okay, a summary, the same pattern of cognitive impairment was seen in the rat. The increase in the level of DNA damage in rat was similar with data that was applied in human. This is very interesting because what we can do now, we could match the data from human and from rats. So from human, we look at the blood profile, and from the animals, what we could do is we could dissect the brain tissue, and then we can do the same thing that we do for human. And then we can compare the data that we have from these two organisms. Okay, so just a bit of more study. Just a quick snapshot of data. So I think in the earlier presentation I showed how your lifestyle modifications, your nutrition, and then supplementation would modify the rate of cognitive decline possibly. So what we do is we also look at Alzheimer's disease mouse model, double mutations. So I just keep this one, it's been clear in the literature that one of the causative factors for Alzheimer's disease is oxidative stress. So what we want to see is whether antioxidants, the one that we are interested in is the vitamin E, tocotrienol-rich fractions, would delay the progression of cognitive impairment. And this is basically a study that currently been taken in Japan, where they are giving antioxidants in 3 different groups, because amyloid pathology means that this is the early stage of Alzheimer's. They still give antioxidants, followed by the later stage with the tau pathology, so they start introducing antioxidants. Even in the worst case stage of Alzheimer's disease, they still give antioxidants. They are trying a different staging of the Alzheimer's disease. So we have tocotrienol-rich fractions. It's extracted from palm oil, so it's natural. We know that it's a potent antioxidant and anti-inflammatory and anti-cancer, and it also possesses neuroprotections. Basically, this study was inspired by a study in the US by Institut in 2014, where they look at tocopherol. Tocopherol is another form of vitamin E, but they use a synthetic form of alpha-tocopherol, and they show quite a nice data where they can delay the progression of mild cognitive impairment, or MCI. This is our design. I'll skip this one. Again, the same thing that we do. This is just the numbers, open field data, so we can show that although tocopherol shows better, but if you look at PRF, it's still a significant difference compared to the AD control without treatments. The path length, again, the same pattern, tocopherol exhibit better results. For the relation to novel objects, tocopherol shows lesser response as compared to TRF. Unfortunately, this data is 2 variables, so we have to look back and see how we can identify if there are any problems in terms of data binding itself. Just to show you interesting data from here. So commonly see again, it's a measure to analyze the DNA damage. So we give the supplementation for the animals for 6 months, and then we look at the level of DNA damage, and then we can see TRF can lower the level of the damage and about the same rate with alpha-tocopherol. We do some studies. This is studies that came out with our collaborators in Japan. We look at the effect of TRF on amyloid beta depositions in the hippocampus and in the neocortex. Surprisingly, it's no effect in the hippocampus with TRF, but in the neocortex, you can see a nice reduction in terms of amyloid beta depositions. Just to add more interesting things on our study, we look at the glial activation as well. We use the IBA1 as our markers, and then we can see that in the neocortex, not much difference, but in the hippocampus, we can see that the TRF can reduce the glial activations. So just a summary, animal with tocopherol supplementation shows the effect in open field, but animal with TRF supplementation appeared to show better response in the drug recognition test. Both TRF and tocopherol are able to decrease the level of damage in AD transgenic mice. So TRF may not only act on amyloid beta, but it may inhibit the microglial activations. So just a take-home message so far. Above 60 years old, human subjects show cognitive impairment that potentially associated with increase in the level of DNA damage. We have good animal model that mimic the human cognitive impairment, and then from there we could look at more deep in terms of the tissue analysis, and then this we can do across organisms analysis to identify the potential biomarkers to see at what point we could start to do some interventions. And TRF may be a good candidate for intervention in delaying intervention associated cognitive decline. For further info, I have 4 students that are presenting their posters today, so you can look at their posters and I think they are very happy to answer any questions. Just to acknowledge my team, of course, the head leader, Professor Bandaraya, all the UTM members. We are quite fortunate to have a collaborators from Japan, Chief Minister of Medical Sciences, Professor Dewan, Director of the institution there, and because of the collaboration, we managed to send 3 of our PhD students currently doing their PhD sponsored by the Japanese government under the collaboration project. And then we have Fatia, Imran, and Zikri doing the human study, and Alia, Izati, and Zulaika currently doing the human study. Okay? I think that's the end of my presentation. Thank you.